A very good afternoon to all the family members of IEM UEM group. Today we are having Professor Shubhajit Paul, Assistant Professor in Electrical Department of UEM Jaipur. Right now he is pursuing his PhD in IIT Roorkee. He will be discussing the topic Space Vector Modulated Matrix Converter Fed PMSM drive employing vector control. So Professor Shubhajit, it's over to you. You can now proceed.
Thank you, Sharma sir. Good afternoon, everybody. This is Shubhajit Pal. Most of you probably know me. I would like to forward my gratitude towards Aniruddha Mukherjee sir and Vishwa Chatterjee sir and the whole IEM management team for selecting me to represent UEM Jaipur in this platform today. So as you can see today, my topic is space vector modulator matrix converter FET PMSM drive employing vector control. Just a minute. Yes. The reason behind choosing this particular topic today is that when I was trying to search for a research domain, I always found it difficult, to find a certain genre where I can give a significant amount of work and present it in a right way. So if this particular webinar or talk helps anybody to broaden their spectrum of research, or provide some new people, a new comer to find a good research topic for the future, I will consider my webinar today will be as a successful one. So without further talking, let's get into this particular topic. So this is a list of abbreviation for everyone. Most of it, I think, probably most of you people know, but still, PMSM stands for Permanent Magnet Synchronous Machine. FOC is Field Oriented Control. It is same as vector control. It is just another name. PWM is a pulse width modulation. SVM is a space vector modulation. MC will be I am going to use for the rest of this talk, which represents matrix converter. And by lambda, I am representing flux linkage. It sometimes creates very confusion because in various literature they represent flux linkage with the help of different symbols. So let us consider lambda for today's talk. And other things like voltages and currents are represented by V and I respectively. So those are very standard, and I think all of us are aware of. So that is not going to be a problem. So this is my content. According to the content, we are going to briefly talk about the PMSM motor and its field-oriented control topology, and then we will talk about briefly about these things, and we'll try to specifically focus on matrix converter, which is a topology that enables us AC to AC conversion, and few of their structures and few of their modulation techniques that we are going to talk about, and I hope that is useful for some people. And after that, we will draw our conclusion and finish this talk. Okay. So let's start. Before starting my talk, this is the basic layout. Why I choose this kind of broader topic? Because this can be used for your research, and also it can be used for some kind of product development. So I want to talk about the whole product as a drive system here. So as we can see here, PMSM is the motor that we want to control. We are controlling using a matrix converter, which is enabling us that AC to AC conversion. We have used our input filter at the input side. Why? Because matrix converter is very prone to disturbance at the supply side. So we need some kind of input filter to filter out those disturbances. Then from PMSM motor and the using some sensors, current sensors basically, we are sensing the currents and rotor position and putting through controller. This PLL block basically gives us the input phase angle. That means if the supply is a three-phase supply, there is a particular angle between all these voltages. So that angle it will extract and give to my controller, which is shown as here PWM driver. But we are going to talk about another advanced topology or advanced controller like SVM that we have already mentioned in the topic of this talk. Okay, and this PWM driver actually providing the switching sequences to our matrix converter, which will in turn will control the PMSM motor. So this is very basic layout, and these are interchangeable. In a way, you can use some other kind of topology in place of matrix converter. You can use some other kind of motor in place of PMSM. So that is up to you, depending on your applications. You can select those things. But this is the broader, block diagram representation or schematic representation, you can say. Next, why we are focusing on PMSM? Conventionally, we most of the time we use DC motor, or most of the time we use induction motor kind of system. But PMSM is day by day taking its popularity, and it is finding huge amount of application in various high power and better dynamic performance drives. PMSM is very the most favorite one nowadays. Now, what features makes this PMSM very attractive? Now, the main thing is PMSM is, by its name we can see, it's a permanent magnet synchronous machine. It's a synchronous machine that is using permanent magnet in its rotor, right? So there is no winding in the rotor. Okay, there is only simple permanent magnet is there. So you can realize, even if you are not from electrical domain, there is no winding in the rotor. There is only your permanent magnet. So the complexity of the whole machine is very good. At the same time, it's very lightweight. Because there is no winding in the in my rotor. Secondly, which makes, and also the inertia of the rotor is also very small, because rotor doesn't have any windings. So the control is very smooth. The operation is not at all noisy, and the torque to the inertia ratio is also quite high. And low speeds, at low speed, PMSM is capable of generating very high high output torque, which is very essential in case of like applications like electrical vehicle, or you may be basic industrial trolley system or lift system. These are very attractive options to have. Now, secondly, another thing is that because there is no winding in the rotor, there is no current flowing in the rotor, right? So if current is not flowing, there is no copper loss, or there is no kind of loss in your rotor side. So this less losses makes the overall machine very efficient. Okay, so these are a few points or features of PMSM which makes it very attractive, and it is very cutting edge. You can lots of people is working on this PMSM kind of motor, its performance improvement, or its control strategies that you can consider for. So this is the steady state modeling, is very straightforward. Per phase modeling is represented here. A simple voltage VA is our terminal voltage, E is the induced EMF, R and XS is representing the resistance and inductance of the stator side. So there is no problem with that. It's a very simple one. And as a vector, we can write using KVL equation. We can write this equation also, like VA equals to EI plus. It's a very straightforward KVL equation. So that would be representing the steady state modeling of our PMSM. This is the torque equation of our PMSM. We will get into this torque equation in detail briefly, but for now we can see that lambda AF is the magnetizing flux. Okay, and we are using permanent magnet. So this magnetic flux is always there, and it's a fixed, it's a constant parameter. And with that, the induced EMF is lagging by 90 degrees. And IS is the stator current, which is also having a particular angle with the EA. And if you add the drop in the stator winding, and if you add this drop with this EMF, which is J into XS IS, you will get the terminal voltage V. And from this torque expression, we can see that lambda F is the fixed constant flux. So there is no control whatsoever in that parameter. IS is the stator current, and sine del dash. Del dash is the angle between IS and lambda F. These two parameters are the actual controlling parameters to control the output torque, or electromagnetic torque produced by the motor. By controlling these IS and delta, we will try to control the torque, and in turn we will be able to control the speed. So that is our end goal. But let's move forward. This is a dynamic modeling. It's the same kind of equations, just we are representing the three-phase voltage equations with the three-phase currents, and it depends, you know, in electrical engineering, all the voltage and currents are dependent on the time, which is a sin omega t kind of term. So there is a ddt term. So we are representing the whole equations in terms of time, and the three-phase equations are also can be represented like a matrix as in this particular equation. So let's move forward. Now we are transforming the whole equations in rotor reference frame. Now rotor reference frame is a topic of generalized Bayesian theorem. Now what we actually do? We take two reference frames. We usually define them by dq if that reference frame is moving. If this reference frame is not moving, then we usually define them by alpha and beta. Now the question is that why we are interested in transforming all of our equations in this kind of reference frames. Now the main advantage we get if we transform all our voltage and current equations to a rotor reference frames means to a reference frame which is rotating with rotor speed, right? Now what is my rotor speed? We are talking about a synchronous motor. So this speed is nothing but a synchronous speed, right, which is basically rotating in a speed of omega s, or you can say it is rotating in a speed in which the stator voltage and current is also rotating, right? So now what advantage does this provide to us? Now if we don't transform our equations to rotor reference frame, what will be the case? All the stator voltage and currents will come as a sin omega t term. That means all voltage and currents will be variable of time parameter, right? Now the moment you are transferring all these things in rotor reference frame, what happens, because this reference frame is itself rotating in the synchronous speed, the relative speed between these two are zero, which in turn will make this voltage and current time dependent AC quantities will actually become DC quantities as shown in this equation as VQS and VDS. Now what is DC? DC is very simple, DC doesn't change with time. So whenever a parameter is not changing with time, dealing with those kind of parameters are much better than dealing with the parameters which is dependent on time. So that advantage will be provided by transforming all this equation in rotor reference frame. So these are the voltage equation VQS and VDS. That means VQ and DS, this is two reference frames and their voltage equations. Lambda QS and lambda DS is Q axis flux linkages and D axis flux linkages. The next one is just in a same equation we are representing using a matrix, so that is pretty much same. And but now the torque equation is represented in terms of these reference frames parameters. Now what information does this new representation of torque equation gives us? It gives us two things. We can see in this talk there is two particular two form, like this is the first form and this is in the second one. The first one, lambda AF into IQS R, this is representing the field component of the torque, right? Like that means this portion of torque is there because of your field. And the second part, which is LD minus LQ into IQS into IDS, it is a reluctance component of the torque, which means that even if there is no field, your motor is capable of delivering some torque to you, which is a very fascinating kind of understanding. Even though you don't have any field in your motor, it is capable of giving you some rotor. Now there are some motor which is known as switch reluctance motor or reluctance motor, where they only use this second part of the torque. Okay, that is another topic for another talk, but now we are going to focus on PMSM. And this PMSM, we can see its torque has two components. One is field component and another is reluctance component, right? Let's move on. Now we are getting into field oriented control, or also known as vector control. This vector control is very advanced control strategies for motor. It is applicable for most of the motors. All motors you can take and apply field oriented control. It has some of its own advantages. So we will look into that, what advantages this kind of control gives us and how we can apply it. Now see, look at this torque equation. Now this torque equation is very familiar. Few slides ago, let me show you this particular torque equation. This particular torque equation, you can see this is very similar. This torque equation and the torque equation I am showing right now is very similar. What is the dissimilarity? That is that sine delta dash term is not there. Now why it is not there and why we are omitting this? Now look at this phasor diagram. Now we have this field line which is lambda f, and this is our is that we have already explained in previous phasor diagram. This is the stator component of current. Now you can, this is we have transformed everything into rotor reference frame. So this is broken down into two components. One is IDS, this one, and one is along this, which is IQS, which is represented here like this IQS. Now see, if this del dash we keep on increasing, say we are increasing this del dash, right? This is moving towards this Q axis. Now if we increase that and we make this del dash equals to pi by 2, if we make if we make this pi by 2, this I of d dash term will vanish. Because this is 90 degree, this will be 90 degree, and IS's term will be IS cos phi. Cos 90 will give you 0, so this IDS term will not be there. Only thing will be there will be IQS. That means if you make this del dash equal to pi by 2, positive pi by 2, then your IS is basically equal to IQS, which is basically equal to IT. IT is termed here because it is representing that torque component of current. Now, and the moment we make this sine del pi by 2, sine of 90 is 1. Okay, so this equation is written keeping this fact in mind that del dash is 90 degree, right? So that is why we have neglected it. Now why we are doing it? We are doing this because the moment this IS becomes equals to IQS, this IQS, what I told you, it is the torque component of the current. So we can actually control the speed of our PMSM motor by only the changing the IQS term, and it will not affect your field. See, why we are doing it? For the most attractive feature of a DC machine is that the control can be decoupled into two sections. One is field control and one is armature control, because those are physically decoupled. But for other machines, AC machines, three-phase AC machines like induction motor or PMSM or any other machine, this decoupling, physical decoupling of the winding is not present. So using this FOC, we are actually decoupling this stator current into a flux component and one torque component of current, and we are taking a particular situation where this flux component is 0. So by controlling the torque component, we can control the IS, and if we can control this IS, we can control this torque and in turn the speed, right? So this is the motoring operation. If you take this del dash as minus pi by 2, okay, this torque will come as negative because sine of minus 90 is minus term will come, and that will give you the braking portion of the you can explore the braking portion also. And another thing is that the field weakening is also very attractive feature. Field weakening portion can also be done by making sure this IS is between this Q axis and this VDS. If we keep this IS in between these two axes, then this IDS will reappear and it will act in the opposite direction of this lambda f, which will demagnetize the flux, and we will get into the flux weakening zone, and we will be able to get a speed which is higher than the base speed, right? So this is the basic understanding of vector control. Now, what advantage it gives us? One is the control is very simple. Decoupled control can be achieved just like a DC machine. Secondly, efficiency is very high because we are continuously changing the stator and rotor field, and using that we are getting the torque. So it's very efficient process, and efficiency of the overall PMSM machine will increase. And sensorless, and okay, fine, sensorless I will talk about later. Let us move on. Now I want to give you the whole picture. Okay, like how can we implement it through my MATLAB simulation, and how can we go from there to our hardware. So if you see that this is a particular block diagram, right? Now we have used all the equations I have shown you to get this block diagram. What I am doing, it's not that difficult. Okay, it may look a bit complicated, but it's not that difficult. Now this particular portion is flux weakening portion. If we are not using flux weakening, this ID star I already told you will become 0. Right? And what is this IQ star? I am sensing the rotor position, and I am doing the operation of subtracting from the reference speed which you want your PMSM to run. Then I am putting it through a speed controller and getting the torque equation. From torque equation, I am using the same torque equation and dividing it by K1 and lambda F. We have already seen this equation, right? Just this equation, I am dividing this torque by this component, so I will get this IS, right? Or IS is equals to IQS. So there it gives you IQS. You put through another controller and you will get the voltage references for D and Q axis. Those you will put through the transformation matrix, Clark and Park transformations, and you will put it through some kind of controller, SVM we are going to talk about, and this will create your switching for your matrix converter. So it will control this matrix converter, and in turn matrix converter will control this PMSM motor. So this is a closed loop control using FOC for a PMSM motor, right? And if you want your flux weakening zone, it's simply you are making sure this ID star goes into negative. You can see this from this field weakening program block. It is 0 usually. If I am using this, it will make it go towards negative. Okay, so we will be able to weaken our flux, and we will be able to address the flux weakening zone. Right? So this is our block diagram. Okay, if you want to ask me some questions, you can write those things down. I will address them at the Q&A section of this talk. Okay, so moving on, now we have established the control of this PMSM motor using an advanced control strategy. Now we will move on to our actual thing, which is matrix converter. What this matrix converter is doing? See, this is a 3-phase AC supply, and I am giving a controlled AC to PMSM according to our reference speed, so that this PMSM track this reference speed. Right? This is a simple, realization of this particular block diagram. So, what is this matrix converter is actually doing? It is actually converting AC to AC. Right? It is taking a fixed voltage, fixed frequency AC, and it is converting it to a variable magnitude, variable frequency AC. So there is a AC to AC conversion we are achieving using this matrix converter. Now, why matrix converter? There are development of AC to AC conversion are still there for last 20, 30 or 50, 60 years. So why all of a sudden matrix converter? So let's dig into the history of AC to AC conversion topologies a bit, and then we will focus on the matrix converter. Let's move on. So this is the AC to AC conversion schemes from low to high power drives. There are two kinds. One is direct converters, another is indirect converter. Indirect converter uses some kind of energy storing device which is known as DC link capacitor. We will talk about it a little bit later. And under that, the normal, very conventional circuits like VSI, voltage source converter, current source converter, CSI, or various modulated inverters like PWM inverters or SVM inverters, or even under VSI there is multi-level inverters, two-level inverters. Okay, these topologies come. This multi-level converter, in this regard, I would like to tell you, this multi-level converter is also very cutting-edge kind of, topology. So if anyone want to, put some effort into it, you can. It can actually help you. But today's topic is not a multi-level converter, which is matrix converter, which come under the direct converters. These direct converters does not use this DC link capacitor or any kind of energy storage device. Under this, there is two kind of topology. One is cyclo converter, another is matrix converter. This matrix converter has again two types. One is two-level matrix converter we are going to focus on, and another is multi-level matrix converters. This multi-level matrix converter you will find very less literature available. There are some work and people are also working on it, but it's not that much investigated properly. But two-level matrix converter is actually various researchers are used nowadays, and a lot of work is being done to improve this matrix converters performance. Now, but apart, we have all these options. Why we want matrix converter? Now, predominantly, what we can to get a variable AC, we can use a VSI kind of topology just shown here. Here, what we are doing, we are converting the DC to variable AC, right? Now, the problem with this kind of, this is very popular and we are using this for last, maybe more than 1 decade. But the problem here is that, you need a DC source, and usually DC source is not available all the time. Most of the time, it's AC source is available. So from DC to AC, this creates a problem for us. To solve this problem, we have moved on to a diode rectifier based VSI type of topology, which is shown here. What we are doing, we are using a diode rectifier. Using this rectifier, we are converting the AC to DC, storing it in a DC link capacitor or energy storing devices. Using that, we are feeding the DC to our inverter, and this inverter is, or VSI is giving you a variable AC. So there is actually AC to AC conversion, but there is, you can see, there is 2 stages. Now, problem with this kind of circuit is that there is more switches, more steps, so loss is high, right? Secondly, this input current and output voltage has a lot of distortion. The power quality is very inferior in this kind of topologies, and these in high performance drives we cannot really rely on this. And second of all, when you are talking about drive, we always want 4-quadrant operation, and here due to, see, we are using diodes, okay, so current cannot go in this opposite direction. Current only can come from this to this. So the feedback of energy, feedback of power from this side to this side is not possible. This is voltage source converter back to back connected with a voltage source inverter. Here this is fully controlled rectifier we are using. So here current can flow in the reverse direction, in the both direction it can flow. So using this kind of circuit we can achieve 4-quadrant operation, but still the input current distortion and output voltage distortion is quite high, and it will affect your high performance drives. And also we are using some DC link capacitor or energy storage device. Also we have to use some filter element, which is inductor, to minimize these disturbances. Now these inductors or this capacitor will be in huge size for a full on high power drives. So it is very difficult to implement this kind of circuit in case of a high power drive or high performance drives. And another point I would like to make is that this capacitor, DC link capacitor, has a certain amount of lifespan. So if you using this kind of all of these direct kind of topologies, you have to keep on changing, keep on maintaining. Your maintenance will increase. You have to check and change these capacitors and inductors over time. So it is not very easy to use this kind of topologies. So what is my next option is the direct one, right? Under direct, we have already talked about cyclo converter and matrix converter. This is a cyclo converter topology. Here AC to AC is possible. Now what is the problem with cyclo converter? The problem is that the input side frequency can be reduced in output side, or the output side frequency will always be an integer multiple of the input side frequency, which is a very odd situation, because when you are using a V by F kind of drive also, you need a variety of frequency in the output side, which is not exactly possible with this kind of circuit. It is possible, it can be made possible if we use force commutation type devices. That means all of these switches are being commutated forcefully according to your need. Now you can see there is whole lot of switches, and if you try to do that, the whole control strategy of this topology will be very complicated, and implementing this will be very difficult. And apart from that, the input side distortion, input side current distortion, and output side voltage distortion will still be there, and the power factor in the input side will also be very high. Those are the features that cannot be accepted in case of high power drives. So cyclo converter may be used for low to at most medium power drive, but for high power drive, this kind of cyclo converter topology is not suitable. Now from here, our concept of matrix converter comes into place, right? So you can see this is a simple matrix converter. Here we are using 9 bidirectional switches. You can see these are the 1, 2, 3, 6, 9. 9 switches we are using. All of these switches are bidirectional. Okay, these are not normal switches. These are bidirectional switches. What do I mean by bidirectional switches? These switches are capable of blocking and conducting voltage as well as current, right? So these are peculiar kind of switch. You will not find this switch in market. You have to make these special switches. Let's go to the next slide, and this is kind of these are the configuration of realizing this kind of bidirectional switches. These switches are shown using IGBT, which is mostly we use nowadays, but they can be made using MOSFET or any other power electronic switches. So this kind of configuration is being used for each of these switches. Keep those things in mind. Now what we are trying to do, we are trying, and another thing, what, there is no DC link capacitor, you can see. So absence of DC link capacitor reduces the weight, makes the overall system compact, so the power density of your overall system increases, so that is a huge, again, low maintenance will be another feature, because we are not using a DC link capacitor. And another thing is that what we are trying to do here, by creating some modulation techniques, we will use these switches as such to synthesize my input side current and output side voltage, and by doing so we will be able to get a proper sinusoidal waveform in the output side, even though there is some inductance in the circuit. We always know if inductor is there, there must be some kind of distortion and their power factor will be less. That is not the case. That we can totally overcome using this matrix converter. We can get a fully unity power factor in the supply side, and the distortion of the input side current and output side voltage will be very less. So harmonic problems, power quality issues, we can be neglected using this kind of matrix converter. Let us move on. These are the features. Mostly I have already talked about these things. You can read if you want, but I have already covered these things. Okay, bidirectional power flow is possible because you can see these switches actually capable of bidirectional voltage and current blocking. So 4-quadrant operation is possible. The design is compact, the power density is high. All these things we have talked about. It has some limitation. One of the limitation is what? The voltage transform ratio is 0.86. That means if in your supply side you have 100 maximum volt of AC, you will get 86 only in the output side. You cannot get more than that. If you can design something that is capable of giving more than 8.6, you will get transaction paper without no problem. So that can be also a future work. And another limitation is that I have already told you, matrix converter is sensitive to the disturbance of AC mains. So we need to add some capacitors, sorry, not capacitors, filters in the input side. This is a direct kind of topology, direct matrix converter. Another one available is indirect kind of topology. This is the same, only difference is we have separated the rectification and inversion mode. This inversion mode is a normal bidirectional switches is not required. So simple available VSI module you can use to create this kind of circuit. So your making of this matrix converters for this kind of indirect type is a bit easier. The features are very similar. Okay, everything you can do with this kind of circuit also. Let's move on. This is we have already talked about. We are this, you can see this is the output voltage, output voltages, these output voltages, and this is the input voltages, this VA, VB, VC. We are going to synthesize this output voltage according to our need using the modulation of each and every switches. Those are represented using a matrix formation. This is same for input current. Input current will also be synthesized from output current using the same transformation modulation technique or switching steps. Okay, so let's move on. Now, direct space vector modulation. What is actually direct space vector? It's very simple. You can dig into it if you want to. But basically, what we can do, if your voltage or current is symmetrical and balanced, you can always find a resultant voltage with a particular magnitude and with a particular angle placement in the space phasor for various switching combinations. Why, how this is being utilized, we are going to talk about, but this is, for now, that if we have a balanced and symmetrical voltage, we can represent it with an equivalent resultant voltage, or for current, resultant current, which has a particular fixed which has a particular magnitude, and it is in a particular placement is in a space phasor is a particular. Now, moving on, what is the switching constraints? If you see this particular circuit, there can be 512 combination of switching is possible, but all of them are not legitimate. Why so? Because we can never short the input side and we can never open the output circuits. If we consider these things, these are the switching constraints we have to maintain, and if we maintain this, the available switching is 27 left. Now here in this first group, there is probably 1, 2, 3, 4, 5, 6 switching states where all the output terminals is connected to some of the input terminals. It's only 10 to 21 anyway, input terminals, and as a result the output phase voltage vectors that we are talking in space vector modulation just right now is not usable. Why so? Because the resultant voltage from this line to line output voltage will be dependent on the supply frequency, so they are continuously moving in the space phase, so you cannot actually use it to synthesize any reference voltage. So this group 1 switches we never use, it is unusable. In group 2, there is 3 switching states, all are null vector groups. Okay, we also call them null vectors, null voltage vectors. Why so? In here, all the output terminals is connected to a one input terminals, so you are not getting any voltage at the output side, so your reference output phase voltage vector will also be 0. But we also use this particular group because we sometimes need to apply 0 voltage vector. If we are required that, we will use this group 2. Moving on, this is the group 3, and here we have 18 combination of switches, and these are the actual switchings that we are going to use. Now in here, always 2 input terminals is connected to two output terminals is always connected to 1 input terminals. Okay, and if you calculate all those output phase voltage, you will end up, for every switching states, you will get a particular magnitude of voltage and its placement in phase plane, right? Like it is in the 0 plane with a magnitude of 2 by 3 VAB. Secondly, for this one, the magnitude is 2 by 3 volt VAB, and it is placed in 2 pi by 3, that is 120 degrees. So if this one is in this plane, this one will be 120 degree apart. Okay, like this. So we are going to use these voltage vectors to create our reference required voltage. And same thing with happening with the current also. We can see we are also getting various input line current vectors and their placements. This is what we need to understand. Using these output voltage vectors, we are going to synthesize our required output voltage waveform, and using these input current line vectors, we are going to synthesize our required line current with input power factor as 0 with no distortion. Okay, this is the essence of this switchings. So let's see how it is happening. We can see that these voltage vectors and these current vectors are placed here, in various phase planes. 1, 2, 3, 4, 5, 6. So there is 6 active voltage vector. There is 6 active current vectors, and say your reference, your required current is lying here. So what we will do to realize this, you will apply this particular, you will apply this particular vector for a certain time, you will apply this current vector for certain time, and you will realize this reference. Same thing is for voltage. This way we can actually synthesize the distortion free, totally distortion free voltage in the output, and totally distortion free current, and with input power factor as unity in our input side, right? So those features that we have talked about are being realized like this. This modulation technique is known as direct space vector PWM modulation technique for matrix converter. This is another one. We have some time, so let us continue. This is another modulation technique known as indirect space vector modulation. What we are doing for direct case, this was our switching state matrix. Now we are dividing it to two phases. One is for rectification, one is for inversion. In inverter stage, we will synthesize the voltage. In rectification stage, we'll synthesize the current. Same thing that we have already talked about, but those things we can also do separately. Now, how we can achieve that? Now, this picture is given just for your reference, but you keep in mind this indirect space vector modulation technique can be applicable for direct as well as indirect type matrix converter. I am showing you this indirect type matrix converter because visually it is easier to realize. We are going to apply this rectification, which is represented by this particular matrix switching states, and this particular inversion stage we are using this particular switching states. And in the same way, output voltage is being synthesized from input voltage, input current is being synthesized with output currents. Okay, so the fundamental understanding is same, but we are using it, doing it separately. Now for rectification stage, same thing, we cannot short circuit the input supply side, so that gives us a switching constraints, and this is represented by these two equations, like this S1, S3 and S5. At one point of time only one of these three can be on. Okay, no two switch like S1 or S3 or S3 or S5 cannot be switched on at certain point of time, because if you does that, this A and B circuit, if you on S1 and S3 at a particular point, this A and B will get shorted and the system will burn out, right? So you cannot do that. So that condition is being represented with these two equations. Keeping these in mind, again in the rectification side we have 9 particular switching steps. From there, now remember this is rectification side, right? We are from this rectification side will synthesize the input current. So in the same way, this is the input line current vectors. Again, it has a certain magnitude, it has a certain degree, and we are again going to use this input line current depending on these various switching steps, and we are going to get our input side current like formation, that format we are going to get. this is again same thing is being replaced. These voltage vectors are drawn here: 1, 2, 3, 4, 5, 6. Six current vectors, and we also have 3 null current vectors. Utilizing these vectors, your reference current can be any of these 6 sectors, and you can from this we can see, if you are trying to achieve this I, you are applying this I of x. This is this for this ix for this t of dot b of x time, say b of x, this is the duty ratio, we will talk about it, but for the dx time, and we are applying this I of y vector for d of y amount of time, and we are achieving this reference current. Okay, so now already we understood. So we need this time, right? Like for how much time we are going to apply this one, and for how much time we are going to apply this one. These time can be calculated by equating the ampere second equations along this alpha and beta axis, and these equations we can generate dy, dx, dc0. That means for dy time, I am going to apply iy vector. For this dx time, we are going to apply ix current, and for dc0 time, we are going to apply this null, one of these 3 null current vectors. Okay, so using that, we can synthesize this input side current from the virtual DC current. There is no DC, there is no DC voltage, or because we are not using any capacitor, DC link capacitor. So these IDC and these VDC are virtual. Okay, for the sake of understanding, we are representing it like that. So this is my rectification step. Same way, inversion stage, again this switching condition will come. Okay, right? So switching condition, what I have told you, ki output terminals cannot be open circuited, right? So let us go to the circuit and understand what I am saying. I am saying none of these terminals, output terminals, can be open circuited. How come this can be open circuited? If these 2 switches are open at any instant or any point of time, this A will be open. I cannot do that, right? So these are basically in a way complementary switch. These equations are being represented here like S7 plus S8. Only one of these 2 are on, and we have to maintain these switching constraints. Maintaining that, again I am getting here 8 switching step. Now remember, this is inversion stage. So this output voltage vector, we are going to synthesize the output voltage. So again, in a same way, we are getting the output voltage vector and their placements. Again, we can draw the same voltage vector hexagon. Okay, there are 6 active voltage vector. There are some null vector. In the same way, your reference output voltage vector, if in this one of these phases, you can use this V beta and V alpha, and you apply for a particular time of say D alpha and D beta, and you can realize this reference voltages. Okay, now what is happening at the same time? Now we have to understand this 4-2 portion is acting at the same time. So how we can make these 2 portion work, in a tandem, in synchronization? So how can we do that? Okay, I will talk about that in same thing. Just I forgot about it. This duty ratio for this inversion portion are can be calculated in the similar way as the rectification stage. Again, you can see the output voltage is being realized from the virtual DC voltage, and virtual DC current is being realized from output current. Okay, and we know these switching stages. We know this D alpha, D beta, duty ratios. So we can actually realize these equations. So now we have to, that is now get back to what I was saying a bit ago, ki these sectors, current and voltage, they are acting at the same time, the time is same, so they are working in tandem. So you have to understand this voltage reference or voltages and reference currents can be any of these 6 sectors. Okay, so if say they are in a, say for example in 6 sector, I have to apply V alpha and V beta with Ix. If I do that, we will get 2 voltage vectors pairs like V alpha Ix and V beta Ix, and for them I cannot apply the simply D alpha or D X, so the duty ratio for the overall pair needs to be calculated like this. So these are the duty ratios we can use for the overall system. Now how we are achieving this? This is now clear. You see, the output voltage is being realized from input voltage, and the switching states in inverter and rectification side we are using, and for how long, these duty ratios we have also calculated. So all of these we know, right? And input voltage we also know. So we can actually synthesize our required output voltage format. In the same way, the current output current we are not interested, output current we have, it depends on the load. So output current we have, so depending on that we can synthesize the input current according to our requirement. That requirement is no distortion, zero harmonic content, and unity power factor. So again, all of these in this equation are known. So if you apply these things in tandem to your non-bidirectional switches for direct or indirect matrix converter, we are capable of realizing this kind of distortion-free output voltage and distortion-free current in the input side, and we can achieve input power factor at the source, right? So these are the very attractive feature we can achieve in our drive system. So at conclusion, actually, we talked about all of these things, and we can see that the PMSM brings into the table its own features. The FOC brings all the features that we have talked about into the drive system, and all the features we have talked about the matrix converters, that is sinusoidal input output waveforms, minimum higher order harmonics. All these features are written here, are coming to your developed drive. That makes this kind of drive is very effective, especially in high power, high performance drives, which are nowadays required for our high speed elevators, our electric drive, electric vehicle option, applications, or various industrial pulley kind of system, or maybe your conveyor belt kind of system. So application is huge, and the prospect is also looking very good. So this kind of drive is one of the major place of research nowadays, because of these because of these kind of good features. And another thing I would like to say, like in our like intelligent techniques like GAPS, optimizing various techniques and neural network kind of thing, we can also utilize in these switching capabilities. Which can further improve the performance of our drive system. So this is a reference I have used. You can go through these papers and books. These are very recent papers you need to go through if you want to know further. There are so many things left to understand and get. So using these references you can get that. So by that, thank you everyone for your patience for this long talk. Okay, I will be very happy if you have any kind of questions. I will be happy to answer them. Dr. Pradeep Sharma, please.
Yeah, thank you, Professor Shubhajit. It was very nice, extensive research work. Definitely a deep work you have done. My best wishes to you for your future work. I'm just posting the polls. Okay, after that I will see the questions. So I'm posting the first poll. So I request all the participants to, there are two polls, so this is the first one. I request all participants to give the votes. Which motor is suitable for an electric vehicle application? Induction motor, PMSM, BLDC, SRM. So it's already 36%, almost reaching 45. We'll wait up to 60 seconds to reach it up to 50 or 55%. So it is already crossing 49%. Okay, crossed 50%. So I am stopping it. It's already 1 minute and sharing the result. So as you can see, the answer is induction motor is 60%, PMSM is 28%, BLDC 10%, and SRM is 3%. So what is your answer on that, Professor Shubhajit?
The right answer would be preferable PMSM. So
Okay.
that.
Okay, so that means 28% got it right? Okay.
Yeah. So I am not at all effective, probably.
So we'll see the second one, second poll. So this is the second poll. A matrix converter is capable of which type of conversion? Please select AC-DC, DC-AC, AC-AC, or DC-DC. So the polls this time is fast. Almost reaching to 41%. We'll wait up to it reaches up to 50%. It's already 48% now. Still left 13 seconds. So it has reached 50% and the time is also 51%. So closing it and sharing the result. So the answer is AC-DC 62%, DC-AC 20%, AC to AC 16%, and DC-DC 2%. So what is your opinion about this, Professor Shubhajit?
Matrix converter I has already talked about. It is doing the AC to AC conversion for us. So that is the right answer.
Okay. So it means 16%, right?
Yeah, I think so.
Okay. So it's very on a very lower part. So
yeah. So, actually, I would like to add, I am not exactly working on these things, but these are very cutting edge kind of technologies. So people who are working on that, please, you can utilize these things. That's it.
okay.
You can always find more information about these things.
Yeah, you have discussed many of the research gaps in this work.
Yes,
so
yes.
definitely it can be a opportunity for the research scholars also. I have received a few comments, good comments from Professor Madhusudan Vaidya. Thank you, sir, for very good presentation. Okay.
Thank you, thank you.
Yeah. So no more questions are there. So we can wind up now, Professor Shubhajit. Thank you very much. And thanks a lot to all IEM, UEM family members. Thanks a lot. Good day.
Okay, sir. Welcome.
Bye. Bye.